This is going to be quite a detailed look at the first step in respiration, which is glycolysis. Okay, and in glycolysis, right, we start off with glucose, C6H12O6, and we end up with 2 molecules of pyruvic acid or pyruvate. Right, now a couple of things to remember here. We just have a look at this. Right, now oxidation reduction, we normally talk about in terms of electrons. Oxidation is loss of electrons, reduction is gain of electrons, oil rig. In organic chemistry, it's a bit more convenient to think of oxidation as adding oxygen or removing hydrogen. Okay, and most oxidation reactions are exothermic, so let's remember that. So if you burn something, you know that's oxidation, it's very exothermic. Right, we start off with glucose, C6H12O6, and you can see that the number of oxygens has stayed the same. You've got 2 lots of pyruvate, it's got 3 oxygens, but the number of hydrogens has gone down. You've only got 8 hydrogens, you had 12 to start off with there. So it is oxidation. And if you just draw a little energy diagram, which GCSE chemistry, so here we can have chemical energy. So if you start off with glucose, is high up, and you go to pyruvate, 2 times pyruvic acid from pyruvate. Right, you have that's got less chemical energy in the pyruvate, so that would be the amount of energy that is released. And if you just did that reaction, that would be released as heat. But that is not the point of glycolysis. In glycolysis, you need to get the energy from that, converting glucose to pyruvate, and keep it as chemical energy. And so what happens is we start off with ADP, and inorganic phosphate, and also the oxidized form of NAD, which is NAD+. Right, and then what happens is you're going to turn them into the reduced form of NAD, which is NADH, and that's got a lot of chemical energy in it, and also ATP, which has got a lot of chemical energy. So you don't want to waste this energy that you get out here. You don't want to waste it as heat. You want to keep it stuck in the chemicals. And these are the 2 chemicals you get. They get stuck in NADH and ATP. And as you see later, the NADH can actually be in the mitochondria, can be used to generate more ATP. Okay, so that bear in mind, we've got to keep the energy stuck in the molecules, not escaping as heat. Right, so here we start off with glycolysis. So you start off with glucose here. Okay, glucose, and we're going to stick a phosphate group on the glucose there, make it glucose 6-phosphate, and you need ATP for that. So you actually have to put in you have to use some ATP up to get the whole thing going. So ATP goes in there, and the last phosphate on the ATP ends up there on the glucose. So you've got glucose 6-phosphate there, G6P, and then it gets converted to fructose 6-phosphate. Okay, so you can see that's just an isomerism. Just a rearrangement of atoms. There's no oxidation or anything like going on at that. So there's not much energy change in that reaction. It's not really exothermic or endothermic, you know. And you break that bond. See where I've drawn it in purple. You break that carbon-oxygen bond there, and then you reform it so that with that purple carbon ends up there where I've drawn the purple carbon on fructose 6-phosphate. Fructose 6-phosphate then gets converted to, you get to stick another phosphate on. So you've got fructose 6 there, but you've got to stick another phosphate on there. That's called fructose 1,6-bisphosphate. And of course, you probably guessed it, you're going to need another ATP to do that. To get this second phosphate group on there, that needs to come from ATP. Right, then this is it looks a bit confusing. So that's you've got fructose 1,6-bisphosphate, which is a 6 carbon, and you split it into 2 times 3 carbon units there. Again, this step here is not an oxidation or anything, it's just you've got the same amount of oxygens in these two things. Now you notice, right, you see where the atoms come from, so I've color coded them. You know, you've got that blue one there, ends up in the blue one there. The orange, you can see where that goes, and the red, and so on. So if you want to pause that and just see, satisfy yourself where those oxygens, where those carbons all come from, and you can probably see that the break is going to be there where that yellow line is. You break a carbon-carbon bond there in order to make, and then you break obviously there as well to make these two substances. Now you probably can see if you use chemistry that this one is a ketone and this one is an aldehyde. So there's no difference in like oxidation there. They're both equally oxidized. Okay. So what happens is the aldehyde form is the one that reacts in the next step, in this step here. Of course, that means that's going to be used up. Le Chatelier tells us that the position of that equilibrium is going to be moved, so the ketone will turn into the aldehyde as the aldehyde is removed in the next step. Okay. Now, this step, something happens. We actually get some oxidation in this step here, right? Because you can see, right, we have got, that's an aldehyde functional group here, whereas this is essentially a carboxylic acid. You've got phosphate stuck where the hydrogen would normally be, but it's an oxidation reaction. You've oxidized an aldehyde to a carboxylic acid, and so you're going to need an oxidizing agent for that. And the oxidizing agent is NADH, NAD plus, sorry, the oxidized form of this enzyme cofactor, nicotinamide adenine dinucleotide, right? And that's going to get reduced to NADH. So that step, aldehyde to carboxylic acid, should be exothermic, but you don't let the energy go out as heat. The energy is trapped in the reduced form of NADH. Later on, that can be used to drive ATP synthesis. We'll see. Right. Now, we've got, what we should also notice is that we have got another phosphate group there, and that phosphate has come from inorganic phosphate. It hasn't come from ATP. And again, normally you would need ATP to stick a phosphate onto there, but because the energy of the oxidation of the aldehyde into the carboxylic acid, that's used, so you don't lose it as heat. You end up with preserving it as chemical energy. You stuck a phosphate on there, and that can later come off and give us an ATP. Okay, so this is the next step. This is where that exactly does happen. So you get ADP, and that phosphate, the yellow phosphate there, gets removed and it gets stuck onto the ATP. So don't forget, we've so for each molecule of this, you get 1 ATP, but we get 2 of those because that's a 3-carbon molecule from glucose. So we've actually now got back the 2 ATPs that we put in. We've now got them back. Okay. Okay, let's have a look at this next step then. The next step, all that happens is the phosphate there on carbon number 3 gets moved to carbon number 2, so that's just an isomerism step, no oxidation going on there. The third step, right, is, you can probably see there, that is a dehydration. What happens is you're going to lose that OH and that H, and you form a double bond here. Okay, that's called phosphoenol pyruvate, that stuff. And in the final step, this phosphate gets transferred to an ATP, to an ADP to form ATP. So you've got ADP goes to ATP. And again, there'll be 2 ATP molecules there because per glucose, because this is a 3-carbon unit, and glucose gives us 6 carbon units, so we get 2 of those. And that's the final product. There's pyruvate. It's just like, obviously if there was an OH on there, there'd be pyruvic acid. We just call it pyruvate because in pH of the cell it will be like that. So let's see what we've done there. Right, we have put in, so I'll just shrink this a little bit. Let's see it all at once. We do a little audit of what's going on. So I'll just do a different color here. All right, so we put an ATP in there, so that's 1 ATP in, another ATP in, so we're down 2 ATPs. But here we get 2 ATPs out. We get 2, sorry about that. We get 2, had to go and see a man about a dog. Right, we get 2 ATPs out there because there are 2 of those for every 1 glucose, so we're now broken even. And then here we get 2 more ATPs out. So net gain here is we've got plus 2 ATP per glucose. And we've also got this NADH here as well. And that NADH later on, it goes into the mitochondria, can give us 3 more ATP molecules. Okay, but that's later on. Now let's see what's happening is, have you noticed that so far here, we haven't needed any oxygen, okay? So up to pyruvate, that is entirely, up to pyruvate, that's anaerobic. Now, you can have anaerobic respiration. The problem is that you're going to, in anaerobic respiration, you're going to run out of this stuff, NAD+. That's the oxidizing agent you need for that step, and you'll exhaust that. So if you want anaerobic respiration, that has to be regenerated. And the way that is regenerated is, this gets turned into that's an acid there, it's a solvent acid, and you can see it's actually called lactic acid, it's lactate. And you can see that you have turned a ketone group into an alcohol group, a secondary alcohol. So that is a reduction. You need a reducing agent for that, and the reducing agent is NADH. And that will be turned back into NAD+. So that's what happens in anaerobic respiration. This NAD+ is used to go back there. Of course, in aerobic respiration, you don't waste the N, that's a waste of NADH. In aerobic respiration, this will go into the mitochondria, where it will be oxidized by oxygen ultimately, and you will get some more ATP made.